Hi, I'm Elijah Honam Akakpo, a postgraduate student from the University of the Western Cape, presenting on the title Optimization of Scintillation Properties of Plastic Scintillator using Jansport Simulations. The content of this presentation includes an introduction, Jansport simulations, results of the Jansport simulations, conclusions of the Jansport simulations, and an experimental setup to test the results of the Jansport simulations. Current PET and PET-CT scans operate on the principle of measuring time coincidence of annihilation events, where a positron from the radioactive source annihilates an electron from the human body to produce two 511 keV annihilation photons. The coincidence window is the time difference between the detection of the two gametes from the annihilation event and the possible location of the annihilation event can also be determined or estimated from the expression dx is equal to c dt over 2, where c is the speed of light in vacuum and dt is the coincidence time window. Signal acquisition and processing in PET system is heavily dependent on the type of scintillator, electronics, the type of digitization, and the signal processing method that we use. The whole process can be divided into two, where we have the optics and the optoelectronics. In the optics system, we have the emission and transfer of optical photons in the scintillator, whereas the optoelectronics system is made up of the sensor and the readouts, where the optical photons are detected by the sensor and then finally read out through the electronics and then processed. The number of optical photons emitted by the incident annihilation gamma is completely random and can be statistically determined by a probability distribution function called the emission function. In the distribution function, tau decay and tau rise are the respective decay and rise time of the scintillator, whereas t and theta are the emission time of the optical photons and the interaction time of the annihilation gamma. The number of optical photons transferred to the photosensor is slightly lower than the number of optical photons emitted by the incident annihilation gamma. The difference is as a result of some of the optical photons escaping, some being absorbed, and some re-emitted. The re-emission of the optical photons is due to the type of reflectors used, the type of the coupling compound used to couple the photosensor and the scintillator, the light guides, as well as the dead regions. The number of optical photons that actually arrive at the photosensor can also be statistically determined by the distribution function P subscript T, where the expectation value of the number of optical photons arriving at the sensor is given by the expression Na equals eta times the expectation value of the number of optical photons emitted by the incident annihilation gamma. Finally, the number of optical photons that are actually detected by the photosensor is also slightly lower than the number of optical photons that arrive at the photosensor. This is due to the loss of time information in the sensor as well as the electronics. The number of optical photons that is detected can also be statistically determined by the distribution function P subscript TD. The Jansport simulation took into consideration certain characteristic properties possessed by scintillators used in PET and PET-CT scans. These characteristics include high light output, high time resolution. The scintillators must be radiation resistant, they must have high atomic density, they must be physically robust, and of course, the cost of production must also be low. Plastic scintillators in general possess most of these qualities except that of the high atomic density. To make up for this deficit, a slightly larger scintillator volume is used. The properties that we considered when we were looking at the plastic scintillator includes the density of the scintillator, the refractive index of the scintillator, the scintillation yield of the plastic scintillator, rise in decay time, and then the gamma that we simulated was a monodirectional annihilation gamma 511 keV, and the number of gammas were 20,000 gammas. The properties investigated during the GEANT4 simulations include the geometry and thickness of the scintillator, as well as the reflectivity of the wrapping material used in the simulation. The geometries investigated include a triangular geometry, a square-shaped geometry, an octagonal-shaped geometry, and finally a cylindrical shape. A snapshot of the scintillation here, where we have the green light representing the annihilation gamma, the blue inside here represents the optical photons, the square cube represents the scintillator stick, whereas the dense blue here represents the Compton event that we are going to measure, and the gray outside here represents the wrapping materials. During the simulation process, we measured the number of optical photons and the time the optical photons were Compton scattered in the scintillator. The first property investigated was the geometry, where we looked at the sum of optical photons detected at both ends of the scintillator at each Compton scattering depth within the scintillator, as well as the time difference between the front and the back end at which each optical photon was detected. So as we can see from here, the red line, which indicates the cylindrical shape, gave the highest number of optical photons, or produced the highest number of optical photons, whilst the equilateral triangle produced the least number of optical photons. Now, the response time, where we looked at the time difference, we're looking for the one with the least time difference, where we see that the red line here, which also represents the cylindrical shape, had the least time difference between the two. The next property that we looked at was the thickness or the length of the scintillator stick, where also we looked at the number of optical photons detected at each Compton scattering depth. So we looked at both ends of the scintillator, and then we realized that the highest number of optical photons were detected for a scintillator length of 5 centimeters. As the length of the scintillator increased, the number of optical photons detected also decreases. The time difference between the front and the back end of the scintillator at which the optical photons were detected was also determined, and the least time was found to be the one with the length of 5 centimeters. Finally, the reflectivity of the material used was also investigated, where we varied the reflectivity from 0.9 to 0.975. 0.975 was the optimum reflectivity that could be achieved in the lab. So also we looked at the same thing, where we looked at the number of optical photons detected at each Compton scattering depth and the time difference between which the optical photons were detected. So from here we can see that the reflectivity, the number of optical photons detected, increases with an increasing reflectivity. So the black representing the reflectivity of 0.975 shows the highest number of optical photons, whereas the reflectivity of 0.9 represents the least number of optical photons detected. Looking at the timing response, the difference between the front and the back end times shows that the red, which represents the 0.9, gives the highest difference, whereas the least difference is given by the highest reflectivity, which is 0.975. In conclusion, of the three properties that were investigated, the ones that yielded the highest number of optical photons per Compton scattering depth and the least time difference between the back and the front end of the scintillator were the cylindrical shape for the geometry, 5 centimeters for the thickness, and a reflectivity of 0.975. We're currently developing a dark system at the University of the Western Cape to test the results of the GEMS 4 simulation. For the photosensor, we're using a silicon photomultiplier. The plastic scintillator is also made up of the same molecular and chemical composition as the one in the GEMS 4 simulation. And for the reflective material, we're using an aluminum foil. The signal is being collected with the current fastest desktop CAN digitizer with a sampling rate of 5 gigahertz. Thank you. I also want to thank the collaborators, the nuclear physics groups from the University of the Western Cape, University of the Zululand, and the University of York. For the audience listening to this presentation, I say thank you for your attention.